So hello, my name is Matti Koskipää. I'm actually the leader of MBSE expert team here in Euronorth for Dassault Systems. And I'm going to start with the V model again. I kind of like what Olof said, but and also what was mentioned before, that it's kind of like waterfall. I disagree with that, but we'll get back to that later on. But what I want to actually kind of reflect here is that when Lynn talked about the sustainability, it's embedded into systems engineering, if you ask me. People tend to forget that. It's about how systems engineering is really about the life cycle of the system that we're defining and at the end of the day. It looks waterfall, but it's not. We'll get that to later. Then a bit of kind of like off the topic, but we'll get back to this later as well. So there was also a mention from, I think Olof mentioned, that to find the problem early and to fix it, then it's way cheaper. It was also mentioned by Lynn in the sustainability discussion. If you find it in requirements, it's one time the cost. If you get to operations, it's thousands of times the cost. And this is, by the way, from Inco's UK study, so it's not kind of like invented by me. It's a fact. The earlier, the better. And this is the cause for a lot of problems. It's getting more and more complex. You just heard about 4 centimeters and how complex that is to be able to navigate within 4 centimeters. I'm a sailor, I don't care about centimeters. Even if I sail in the Nordic countries where we have a lot of rocks and islands that you don't have in the oceans. But the fact is really that the complexity is massively growing. And again, we get to that fundamentals of systems engineering is a major goal of systems engineering is to reduce the perceived complexity. And that's about it. Then we get to the higher level aspect, because my topic was something related to enterprise architecture and end-to-end architecture, or whatnot was the topic. But this is really the kind of the topic that I want to talk to today. It's about the enterprise architecture. It's about the system of systems definitions, and then going to a system level definitions. In Kongsberg, I know that they get definitions to provide system for a mission, correct? So that's the system of system level discussion. That missile needs to be functioning within an environment of other systems, radar systems, God knows what else. Not my beef, to be honest. And when we think about the V model that we looked before and what Lynn talked about and the goals and the strategies of current enterprises, it's about the architecture. How do you provide a sustainable enterprise? You model the enterprise. You look at the enterprise, what are the capabilities that are required? You look at the operational scenarios that are providing the capabilities for the enterprise. And you could do verification, so long for the waterfall. You do the verification at the very early stages of this modeling. Now the beauty of here is that when we talk about enterprise strategy, they tend to be kind of high-flying, nice ideas, whatnot. The flying unicorn type of stuff. But with modeling, me being an engineer, I kind of like to understand what that means. I can actually start to decompose that complex unicorn into a horse that has been put a fairy wings on top and a horn into a carrot as a horn into the forehead. Now, once we go from operational scenarios down, we start to kind of define the operational requirements, and we get to system of system architecture. And here we can do, again, loop back. We can start doing trade-off analysis for what kind of system or systems within our system of system we need and require. And we actually do proper simulations, we do trade-off analysis, and we can do business and mission analysis. And within, this, we ensure that we are providing the real and the correct solutions for the problem that was defined. Again, basic systems engineering at the end of the day. So here we put that on the V model, and it's not anymore a waterfall, sorry to say. Then we get to model-based, because that was all systems engineering. Now we get to model-based systems engineering. It's about the single source of truth. That's been already repeated multiple times, even in this room, but also in the big auditorium. So everybody looks at the same model. They don't look at the random documents, like Olof said. It also provides the total knowledge for each and everybody who are included in that project or system definition. They get the correct information. They see and they get the knowledge. Again, 20 years for one manufacturer or designing of one missile. You need to have the knowledge in your model. The design decisions mentioned by Olof again. What are the design decisions done 20 years ago that still affect me, and what was the basis for that specific decision to do? There has to be all of that explained. Now, if I would jump into KDA and start looking at their model, I could actually start understanding what was the reason for that specific decision. It might change today because materials are gone forward, software has progressed, all of that has changed since 20 years, but there's still a benefit for me understanding that knowledge as well. Human and machine interpretable. So SysML is a language. We know it's a version 2 coming out soon enough, hopefully. September should, maybe, perhaps, we'll see. But at the end of the day, SysML is still, even 1.7 is still, can be interpreted by also with machine. And like I already said, even I can read it. I'm coming from a mechanical background and I still understand SysML. Well, I did a bit of study on that, but still. Okay. So the benefits from going from textual, so document-based, to model-based systems engineering is quite, again, clear. You do spend more time at the left side of this. So you spend way more time on system design. You spend maybe a little bit, well, roughly equal time on the detail design, but where you get the massive benefits is the integrations and the testing. Because actually what you do is you start doing your testing here, not there. So you do way more testing at the front, at the beginning, on the left side of the process, and you gain time. That actually leads to the fact that, first of all, you are able to identify the risks early, and you can mitigate those risks on the spot, instead of finding them out at the integration level or in the test and implementation level. And that actually leads back to that. With model-based systems engineering, you don't do that. You do that. And that's where the money is from a quality perspective. So what does MBSE require? I was a bit concerned about the previous thing, that you do not have an kind of like a methodology or a framework defined. We're very much willing to help you on that stuff. But what you do need is you do need to have some sort of a methodology in place so that everybody is modeling the same way. Because you can, I mean, CATIA Magic is a fantastic tool. You can use it in so many ways. You should have methodologies to use CATIA Magic. And that's actually where the framework comes into game, because the framework is actually supposed to define you the methods, the rules to do systems engineering within your company. Unified language. Everybody needs to speak the same language. You talked about Asia, US, Europe. The common language is your modeling language, and in your case, it's SysML, and that's what we love here in Dassault Systems, to be honest. That enables, and then the tool, of course, we talk about Katia Magic, let's keep it that way. Then obviously, once you have those 3 pillars in place, then you can actually do a system model, but you do need the people, qualified and motivated people, and that is actually, I'm very happy to hear today that's been a concern to many, because that is by far the most difficult part of the whole thing. How do you get people to do systems engineering, to do system thinking? That was mentioned again as well. So that's where I've failed miserably myself. All the rest is like one person in a customer said, it's just IT. To some extent, yes. That's the difficult thing. UAF. So this is a standard. Don't worry about it. It looks complex. Don't worry about that. I'll explain it a bit later. So this is a standard. Actually, I'll jump back. So we talk about unified modeling language. When we talk about system enterprise architecture, there is another language that is called UAF ML, and it relates to this, which is the Unified Architecture Framework. It is its own language, but it's actually based on SysML. So it's direct extension from SysML. So if you do SysML, you can do UAF. It is for enterprise and system modeling. Specifically, it is a combination of best practices. It's actually combining DoD AF, so Department of Defense Architecture Framework, MOD AF, Ministry of Defense Architecture Framework in UK, and NATO Architecture Framework, but it's also commercialized. So it's actually made into a commercial version as well. So you can use it for commercial and military side. It has a whole lot in there. Nobody uses all of it. So you pick and choose. You have the strategic layer where you define the goals, the objectives and capabilities. Then you've got the operational, which defines how the system of systems perform at the logical conceptual layer. You have the services, and you have resources, where you actually kind of start to understand the system of systems, how the systems actually are related to each other. And then there's the securities and on. Never heard anybody using projects. Somebody might use, but never heard that happen. But it has more of a dimension than this grid dimension. So strategy is also linked to services, not just operations, but also for security, because security is often part of the strategy as well. And the good news here is that there is actually OMG, so Object Management Group, who manages the UAF as like as SysML. They have defined a workflow, and they also have a book called Enterprise Architecture Guide for UAF, which describes how to use it. It's actually very good, to be honest. That's how I've been studying this stuff. So you take the book and start playing with it, and you'll get it. If you're a systems engineer, you know Katia Magic, you'll get it. Don't worry. The good thing about this is that when you do this enterprise architecture and you reach resources level, then we start to get the content for your system of interest definition. Now, Ule mentioned Magic Grid. I hail for that from the bottom of my heart, because that is the Magic Grid defined by or developed. It's a framework for system of interest definition by Dassault Systems. A lot of experience into it. It's written by people in Dassault, verified and reviewed by customers. So and by the way, it's free, so go get it. This 350 pages roughly. But actually, there's a direct link from this enterprise architecture to the Magic Grid. So this is the Magic Grid. It starts to look at this from a product perspective or system perspective. Now consider that this system that we're defining here is part of your product portfolio, Well, where did you define your product portfolio? Well, you did it in your enterprise architecture for sure. Because your product portfolio is your resources as a company. That is the key asset of your company. If you don't have it, you don't have the company. Enterprise does not exist. And as you can see here, it's kind of it's a PowerPoint, so it's not kind of like free. But the fact is that this flow is more or less seamless. Then you can start breaking down your system into more simplistic cases. So obviously we simplify the complexity like systems engineering is supposed to do. Little bit of an example of the enterprise architecture part. We're not going to go to that deep that you just saw. We're just going to scratch the surface on the enterprise architecture actually, because I'm running out of time apparently, I suppose. So this is how it looks. So we have a strategic motivational diagram of energy to hydrogen or green hydrogen. So we have opportunity. There is no green hydrogen production or it's limited. So it's giving us a motivation, and there's a driver, which is the shipping industry demand for clean energy. Shipping industry is one of the most polluting in the modes of transportation, and we use shipping a lot. Nowadays, the ship engine manufacturers are moving more and more to green energy. How do you change a massive, 2-story building size engine to green? It's a combustion engine. You put something green to burn. Kind of sounds funny, but yeah. So we have a challenge to produce enough green hydrogen. So it's also an opportunity and driver for us. So, but because we are talking about green, we need to see how does this green energy affect our biodiversity? How does it comply with the government policy for clean energy, etc., etc.? So all of that level aspects we actually start to model within this. And this is kind of like where it leads to. We have 2 wind farms, offshore wind farms, north and south. We have undersea cables for sure, because we need to connect to the port, where we actually start the hydrogen production. But we might actually sell the excess energy to the grid. Or sometimes we actually might need more energy because these are not rotating. We need more energy from here to do that. We don't know it. That could be a scenario. So we're actually looking at the layer 1 where we really look at the enterprise architecture, like we talked about, the drivers, challenges, opportunities. And then we start to look at like design options, constraints. We don't know what these are. We have no idea what they are at this point. We only generate energy from wind or offshore. That's all we know about that. So we use trade analysis and requirement validation for that. So this is actually the same model in Katja Magic now, where we actually start to look at how do we get that. So we look at the strategies and the opportunities that provides, and how do we actually put that in here. So we have the offshore turbines. Now we actually here can start to consider what kind of turbines we can have and should have. So we have different options for the offshore turbines. Not going to go into details. Some are higher than the others. Some have, meaning that they have a bigger wingspan, which means they produce more. But on the other hand, they are high. So we might have regulations that they're not allowed to be that high. But those are all, so we have 850 feet. They have a cost. So now we're actually getting to the situation where we are defining the business case, modeling the business case to which kind of wind farms do we want to do. And that's actually where this originally initiates. There's a customer who wanted to understand, is it feasible? Now this is a very simplistic example of that business case calculations that we actually would want to do, but then we kind of go beyond the border of what can I tell and what I can't tell you guys. But at the end of the day, we can define the weightings of different attributes, and we actually start to simulate which is the best combination of systems within our system of systems so that it actually complies with the regulations as well as our goals for the enterprise. I cannot speed this up, sorry, from here. So basically we did that. Now that we kind of have the basic concept, we can go one step further down. We start to look at the system behavior, the interactions, techniques of how to do it. We do system of system simulations and Monte Carlo simulations for to go down and narrow down the different options that we've got. How, for example, if we have what is what's the word in English? The operational time. So if it's if you have a wind turbine that is turned off for whatever reason, maintenance or whatever, we can start to kind of calculate also these worst case scenarios, that if we lose half the wind turbine, then what? We can't turn off the hydrogen production. We need to get energy from somewhere, and our business case just fell to pieces. Not sure when I was supposed to stop. Okay. Because I have another video where actually we start to calculate all of that. I don't know if you're interested in it, so I'll put it running on the background. But the idea here really is that too few companies, enterprises, actually look at themselves and model themselves. The good thing also about the enterprise architecture and the UAF, it is kind of time dependent. So it's an evolving thing. You know, a CEO changes, strategy changes. You go and change the model. And so on. But then again, even if the strategy changes, the portfolio might not change the same day. It might take a bit of time if you even want to change the portfolio. The thing, the main thing here is that you actually again look at this from a problem domain like systems engineering tends to do. You look at the problem, you try to solve it. In our case, in enterprise architecture case, the problem is actually the market kind of, and the mission of the company, and the strategy of the company. And then you can start looking at what kind of, at the end of the day, you can start thinking of what kind of resources you need. So for example, as an organization, do you need more systems engineering? Do you actually need a systems engineering team who is governing your systems engineering methodologies, architecture frameworks, etc., etc.? You need an IT person in that team, perhaps because somebody needs to own the IT systems that support your systems engineering processes. So you can actually even do that. And that's actually what I did for Euronorth, for my team. I looked at Euronorth strategy and turned that into my enterprise architecture, where I look at like what my team as a systems engineering team has to have to provide the needed services and capabilities for Euronorth, Dassault Euronorth organization. So we're actually using this and doing that as of today. Any questions?
Right.
Thank you.